Okay, so I'm going to put up the document camera so that we can follow along. And you should have received a copy of the protractor, and you should have one laser pointer per table. And you should have a block of some size. Now, the drawing cutout is for a 2-inch by 4-inch block. Your actual one is going to be smaller, or your one that you're using today is going to be smaller. I'm still trying to get the right size block for the right cost. When you're using the laser pointers or the laser levels, you have to be extremely careful not to shine it in the eyes of your fellow lab mates. This is a common thing that happens, so don't turn on the laser level until you're ready to do the activity. The instructions for the activity are going to be printed directly on the sheet itself. So the students in the STEM club, they'll just get a sheet and they'll have the supplies to be able to do this activity. So the way it explains in the instructions, so let me rotate it sideways so it faces correctly. You're going to send light in at a fixed angle. So there's going to be some angle that you pick for your laser level, and that's going to shine light on the block. It's important that the light hit the block exactly at the center of the protractor so that you measure angles correctly. So when the light comes in, it's going to be bent in the same way that we talked about how the swimmer or the lifeguard changes their angle based on the differences in speed. So the light is going to be bent at a certain angle. We want to measure where does the light come out of the block. So a very common error that students make when they do this activity, they continue to trace this ray after it's bent, and they continue to follow it to wherever it hits the exit or wherever it hits the protractor. And that's not going to be the correct angle. What you need to do is you need to put a dot on the sheet of paper. Where does the light exit? Once you've recorded that dot, you lift the block up and you draw a line that goes from the center through that dot to measure the output angle. And then you can estimate the refractive index of the block, or basically how much is light being slowed down, by calculating the ratio of sine theta 1 over sine of theta 2. Okay, questions so far?
Theta 2 is measured from?
Theta 2 is measured relative to 180 degrees. So I would place my block here. I would set my laser level, so the laser level projects a line. So let's say that I'm doing 70 degrees. So, oops, it's off the screen. Okay, so I'm shining the laser light through the center. The block is flush with this edge. The laser hits very centrally. And then I need a pen.
Interesting that yours shows up white.
Yeah, so it's yeah, it's a good question. Why does it show up white? It's a red line. Not quite on 70. All right, so let me get it closer.
There you go.
All right, right on 70, right through the center. All right, so accuracy may not be perfect.
That's the old carpenter.
Yep.
It has to be plumb.
Mm-hmm.
They call it max A, but I ain't gonna say it.
All right, so I've made a dot as to where the light came out, right? So now I would draw with a straight edge from the center through this dot. Oops. And I would mark, probably should extend this axis. So this is theta 2. And this angle is theta 1. So in this case, I would record theta 2 relative to 180 as being 219 minus 180, or 39 degrees. Okay. So my estimate would be sine of theta 1, which is 70, over sine of 39, And someone with a calculator? Sine of 70 over sine of 39. N1 is 1 because we're in air, yes. Air is, it's like 1.00001 something. Try different angles. As a sanity check, if you shine it in at 0 degrees, what should it come out as? Better be 0, better be going straight. There shouldn't be any bending if it's going straight through the block. And see, so think about what angles would give you the most accuracy. Will you get better accuracy if I shine at a very small angle or if I shine at a very large angle? And why? Okay, so what can influence the accuracy of the measurement? So I mentioned that some angles you'll get more accurate results than others. Based on this, do you think small angles or large angles give you more accuracy? Large. So these two are about the same, and this one, like 4 degrees versus 8 degrees, makes a huge difference. And so the reason is that when you look at this formula, you're dividing by sine of theta 2, and if this number is small and your angle is off by a degree, it's enough to completely throw off your estimate. So in a practical application, to understand sort of how measurement accuracy can be improved, you should think about how sensitive is your formula to errors. So when you make your measurements, there's always going to be errors in it. And so what you want to do is work in a region where small errors are not going to influence it very much. So sine of 39 versus sine of 40, it's about the same, but sine of 4 degrees versus sine of 5 degrees, completely different. So steeper angles are much better. Anyone try 90 degrees? What happens if you use 90 degrees? 90 degrees, it doesn't go through the block. If you go slightly less than 90 degrees, like 89 degrees, that's probably the most accurate. The correct answer for this should be about 1.45 to 1.55, depending on the exact material that's used. So what you've learned in this session is that light slows down as it goes through the material, and as a result, it bends or it refracts as it goes through this interface.